Okay, for the common emitter, we have three main bias circuit. The first is the fixed bias, and then we have the fixed bias with emitter resistor. Then the last one is voltage divider. So basically, all of them can be solved using is quite similar procedure. Okay, but for in term of AC analysis, the thing that you need to consider is whether there is bypass capacitor at the emitter resistor, or there is not the bypass capacitor, whether it is bypass or unbypass. Okay, this is two consideration that you need to take into account when you want to do the AC analysis of the common emitter. Okay, so next let's do the example for voltage divider circuit. So this is a common emitter. So this is a common emitter. The input at the base. So input is at the base, output is at the collector. So emitter is unused port or unused terminal. So this is common emitter. And then this is the bias circuit is called voltage divider. So overall, this is called common emitter voltage divider configuration. Okay, so determine the value of input impedance, output impedance, and then we have AV here. We have three type of AV: AVOC, AV, AVS, and we have two type of current gain AI, and we have the power gain here. Okay, and then this is given. The VA is infinity, and IC is 2.37 milliampere. Okay, so the value of IC is very important because we want to calculate the GM. So the value of IC is needed to calculate the GM. So this is GM is equal to IC over 26 milli. Okay, if the IC is 2.37, so that means that the GM is 2.37 milli, sorry, 3.7 milli over 26 milli. So this is equal to 91.15 milli, and the GM the unit is Siemens S, the capital S. Okay, for VA is infinity, so this is related to the small r naught. Small r naught is equal to VA over IC. When VA infinity, so r naught is also infinity. So this is open circuit, so you can remove the r naught. Okay, so this is small r naught GM, and then if you know the GM, you can get the value of r pi. R pi is beta over GM, so beta is 120. So beta is given here 120 over 91.15 milli. So this is equal to 1.32 kilo ohm. So you got this T. These are three main parameters for your mid-band equivalent circuit. Okay, the first after you have calculated the three parameters, you need to draw the equivalent circuit at the mid-band. Okay, so how we can draw this? You can draw starting from the supply here. Okay, let's draw starting from the supply. So this is VS. Okay, after VS, there is RS here. After we have VS, we have RS. This is RS. And then after RS, we have this capacitor C1 is short circuit because of AC analysis. Okay, and then after that we come to this point, this node we have 3, 1, 2, 3. Okay, so this 3 is the first one is R1. So R1, another terminal of R1 is connected to the VCC. So this is ground. So this R1 is actually this ground. And same R2 is also become like this. Okay. And then now we have come to the base of the transistor. So between base and emitter, we have R pi, and then the voltage is V pi. The voltage across the R pi is V pi. And then at the emitter, since we have this bypass capacitor here, so Re can be removed. So this is directly connected to the ground, the emitter part. And then between the emitter and collector, we have the current source here. Pointing downward, the value is GMV pi. Okay, and then since we know that the R node is infinity, so no need to draw the R node. Okay, after that, at this collector point, we have RC and we have the RL. So this is collector point. We have this is RC and we have the RL. So it's RC and RL. So this is the mid-band equivalent circuit. Okay. So after you draw the equivalent circuit, let's calculate the input impedance. So this is input impedance. Okay. So what you see here from the input impedance is R1, R2, and R pi all are connected in parallel. So RZI is equal to R1 parallel with R2 parallel with R pi. So this is R1 parallel with R2 is R1 is 8.2K times 1.5K over 8.2K plus 1.5K. So this is parallel with R pi is 1.32K. So R pi we have calculated in previous slide. So this is you will get this one is 1.27K parallel with 1.32K, and then the answer is 0.647K. Okay, so this is the answer for ZI. For the Z node, okay, for the Z node, you will see only RC. So the Z node is simply equal to RC. Okay. Okay, again, please be reminded for the Z node calculation, we will assume Vs equal to 0. So when Vs equal to 0, the V pi is also equal to 0. So Gm V pi is equal to 0. And then there's no connection at the current source. So at the end, what we will see is only RC. So RC. So Z out is equal to 4.3 kilo ohm. So this is the answer for Z out. Okay. So next we do the AVOC. So for the AVOC is this is when RL is removed. So we remove the RL. So let's say we remove this one. So remove the RL. So what will happen is this is open circuit at the output. Okay. When we remove the RL, the AVOC is defined as the Vout OC, okay, the reading at the output voltage as the output port when there is no RL over VI. Okay, so what is VI? Or in this diagram is Vin. So Vin is the voltage at the input port of the amplifier. Okay, so what is VOOC? VOOC is calculated from the voltage drop at the RC. So VOOC can be calculated using the voltage drop at the RC. So voltage drop at RC using Ohm's law, the current at the RC is minus Gm V pi times RC. So this is equal to you put all the equation the minus Gm is 91.15 millisiemens. So this is milli. So and then time RC is 4.3K. So this is V pi. So you will get this the value is here. So you get this one is minus 391.95. Okay, this is as a function of V pi. And then how about the Vin? Okay, in the emit band equivalent circuit, Vin is actually the voltage across the V1. R1. So voltage across the R1 is equal to voltage across the R2 equal to voltage across the R pi. So voltage across is R pi is V pi. So Vin is equal to V pi. And then when you use the VOOC and Vin equation to calculate the AVOC, you should get something like this over V pi. So V pi can be cancelled out. So the final answer is 300 minus 391.95. Okay, so next we calculate the what is we call it AV. Okay, AV is actually when we insert or when we connect the load to the output port. So this is the output after we having the load over the VI. Okay, so let me copy the equivalent circuit. Okay. Okay. So or maybe I just redraw it back. So we have here this is VS, and then we have the RS is 600, if I'm not mistaken. Okay, 600, right? And then we have here this is R1, and then we have R2, we have the R pi, this is V pi, and then at the emitter is connected to the ground, so this is no resistor here. And then we have here the current source TMV pi connected to the collector port connected to the RC, and then lastly is connected to the RL. Okay, so here the V out here is voltage across the RL. Okay, voltage across the RL is equal to voltage across the RC. So if you want to use the RL, you need to know the current at the RL. But here I use what I do is you combine the RL and RC and then times the this current minus Vm V pi. So we have the V out equation is equal to minus Vm V pi times RC parallel with RL. Okay, so this is minus 91.15 millisiemens times V pi. RC is 4.3K, RL is 10K. So here you should get we calculate this one, R1 and RC and RL, the parallel, the total resistance will become 3 kilo ohm. So 3K times 91.15. So this is minus 273.45 V pi. So this is equation of V naught. Okay, for the V in, so the V in is at the V1. So this is similar to the previous AVOC calculation. V in is equal to V pi. So lastly, you will get AV is equal to minus 273.45 V pi over V pi. So V pi can be cancelled out. So the final answer is 273.45. Okay, this is the AV. Okay, so next we have another voltage gain. We call it AVS. So AVS is V out over Vs. So difference between AVS and AV is the input signal. So the input signal is the supply voltage, not the input voltage at the amplifier port. So here VS. In this AVS calculation, you need to consider the effect of the internal resistance of the source, which is this 600. Okay, how we can do that? So V out. So in this case, V out is you can use the previous calculation. V out is minus 273.45 V pi. So Vs you need to relate it with the V pi. Okay, so you know here the V pi is equal to V in. So V pi is equal to V in. And then V in is a voltage divider between 600 and between the Z in. So we see the amplifier from the input port. We see the resistance of the amplifier from the input port is the Z in. So the voltage drop at the input port will become the I in times Z in. Okay, so that's why we need to use the Z in the voltage division. So VI is equal to ZI over ZI plus 600 Vs. Okay, so you know you can from this equation can rearrange the equation and you get Vs is equal to, so the ZI value is 647 ohm or 0.647 kilo ohm, which is as calculated before. So this is Vs is 647 plus 600 over 647 V pi. So you got this calculation. The calculation is 1247 divided by 647. So you got this one, Vs is equal to 1.93 V pi. Okay, from these two equations, so this is number 2 and number 3, you can solve the AVS. AVS is minus 273.45 V pi over 1.93 V pi. So V pi cancel out, and lastly you get the AVS is equal to minus 141.68. So this is the AVS. Okay, so we have done the voltage gain. Next, we do the analysis for the current gain. Okay, before that, we need to redraw the band. So this is VS, and then this is 600. This is R1, and then this is R2. We have R pi. This is RC. This is the RL. Okay, so the current gain AI. So AI, in the actual question or in the exam or test, the definition of AI will be given, and as well as the current direction. So for example here, I define the AI as the current at the output current is the current at the load. So the output current is the current at the load. So this is IL, and the input current is II. So AI is defined by IL over II. Okay, what is IL? IL is a current division between the RL and RC. You know that the current towards from the current source in the opposite direction is minus GMV pi. So this is the source of the current. So this is minus GMV pi. So the RL, current at the RL is the division from the minus GMV pi. So IL is equal to RC over RC plus RL times minus GMV pi. So you insert the value. So minus the 91.15 times 4.3 divided by 14.3. So this is minus 27.41 milli, and then we have this V pi. This is IL. Okay, for the II, okay, so the II we have II is VI over ZI. So VI is equal to V pi, and ZI is equal to we have calculated the input impedance is 0.647k or 647 ohm. So here we use this equation. Okay, so we have this II. This is, I put this the second equation. The IL is the first equation. So you can solve what is AI. AI is minus 227.41 milli V pi over this is V pi 0.647 K. So lastly, you can get this one is the AI is minus 17.73. So this is AI. Okay. How about another AI, another current gain? We call it AIS. Okay. AIS. If you want to calculate AIS, what you need to do is you need to change the voltage source here, Vs here, into the current source, because AIS is equal to IL over IS. So in this mid-band equivalent circuit, there is no IS, so you need to change it to the IS. So the changing will be from this. This is Vs, and then we have the internal 600 ohm. So you need to change to the, this is IS, and the 600 ohm will be in parallel of the current source. Okay, and then this is the II. Okay, you need to convert for the voltage source to the current source. When you do the conversion, you can have the relationship between IS and II. Okay, the II is equal to voltage division between 600, current division between 600 and the input impedance. So this is a 600 over Zi plus 600 times Is. So Is is equal to Zi is 647. So this is equal to 2.08 II. So this is the third equation. So AIS can be calculated from the equation number 1 and equation number 3. So this is you get equation number 1, 2 and 3. Okay, 1, 2 and 3. So equation number 1 is AIS equal to IL. IL is equal using the equation number 1 is minus 27.41 milli V pi. Okay, and then we have IS is equal to 2.08 II. This is equation number 3. But II is equal to V pi over 0.647 kilo. So this is V pi over so here we can cancel out the V pi, and lastly we get the value of the AIS is minus 8.52. Okay, so this is the answer for AIS. Okay, so we revise, we recall back what we have done so far. We draw the mid-band equivalent circuit. We have calculated the input and output impedance. We have calculated the voltage gain. We have AVOC, we have AV, we have AVS, and then next we have calculated the current gain AI and AIS. So next, from the voltage gain and the current gain, we can calculate the power gain. So AP is equal to AI times AV. Okay, so just simply multiply the AV and AI. So AV is Let me check. AI is 17473, AV is 27345. Okay, so both have the minus value, both the gain is minus value, so the power gain will become positive. So this answer is 17.73 times 273.45. So the answer is 4848.27. Okay. So this is the power gain. Okay. Before at the end, next I want to do exercise converting the gain to unit of decibel. Okay. For example, the voltage gain, we know the voltage gain is AV is minus 273.45. If we convert to the decibel, the equation is log 20 times log modulus minus 273.45. So because we have modulus, the minus is cancelled out. Minus here the value is become 20 times log 273.45. So this is 48.74 decibel. Okay, for the AI, the value is minus 17.73. In decibel, also use the same equation, 20 times log modulus minus 17.73. So this is equal to 24.97 dB. Okay. As for the power gain is 4848.27. The equation for the power gain is 10 times log 4848.27. So here the answer is 4848.27. Okay, so the answer is 36.86.